In this problem, we're to use nodal analysis to find V0. And if we look at our circuit diagram there, you can see where V0 is labeled on the diagram. We're going to use our problem-solving strategy for nodal analysis. And the first step is determine the number of nodes in the circuit. So if we go through, there's one node, a second node, a third node, then there's a node on the bottom. Okay, so we have 4 nodes. And if you look at our problem-solving strategy, it says assign one node as a reference node. So let's pick the bottom node as a reference node. Then we're going to assign node voltages. And we'll have 3 node voltages. And I'm going to assign them as follows. I'm going to call this one V1. This one I'm going to call V2. And this one we'll call V0. Okay, so we have 3 unknown node voltages. That means we're going to need to write 3 equations to be able to solve for V0, V1, and V2. Now, we don't have any voltage sources in this circuit, so we skip our step 2 of the problem-solving strategy. Since we have no voltage sources, we're immediately going to go to step 3, which says apply KCL to the nodes to get our 3 equations. So let's start with this node. Okay, so if I look at currents leaving, so for instance, the current leaving the node in that direction, V1 over 3K. Okay, the current leaving in that direction. And if you remember, we're going to use KVL to get the voltage across that resistor with that polarity because we want the current in that direction. And that'll be V1 minus V2. So we'll have V1 minus V2 over 6K. And then there's the current leaving through resistances. Let's set equal to the sum of the currents entering from sources. So if we look over here, this one is entering. And then this one is leaving. Okay. So here's our first equation. Now let's collect terms. So there's our first equation in this problem. Now we're going to repeat the same at the other 2 nodes. Okay, so here's our circuit again. Again, let's just label things again to refresh our memory. Okay, we've already applied KCL at this node. Now let's apply KCL at this node. So if I want current leaving, so I have V2 minus V1 over 6K. That's the current leaving in that direction. Then we'll have V2 over 6K, which is current leaving down. And then out to the right, we'll have V2 minus V0 over 2K equal to 0. Now let's collect up terms. We'll have minus 1 over 6K times V1. We'll have 1 over 6K plus 1 over 6K plus 1 over 2K times V2. And then we have minus 1 over 2K times V0 equal to 0. So there's our second equation. And if you look at our terms, for instance, If you think about it, this term is the sum of the conductances connected to node 2. This term, we have a 6K resistance, which is a conductance of 1 over 6,000, and this turns out to be negative of the conductance connected between 2 and 1. Now let's do KCL around this node to finish things up. Okay, so the current leaving through that resistance, V0 over 1K. Then we want the current leaving that way. We have V0 minus V2 over 2K. And we have one current entering from the source is 2 milliamps. Okay, so then our equation becomes so there's our two additional equations. Okay, now let's collect those into a matrix so that we can solve them using MATLAB. So there our equations are in the matrix, and then using MATLAB we'll get the following answers. V1 is 13.4545 volts. V2 is 4.3636 volts, and then V0, which is what we're looking for, is 2.7879 volts. So there's our answer.